Okay, to this problem, we know that the speed is given us that 25 meters per second. Okay, and it's moving along the path. That's we already know that the path equation here, and we have the acceleration. Okay. Okay. When we imagine that when we consider the motion of the car, same as we driving a car. Okay, we always has just only one velocity component. Okay, when we observe the speed gauge, the velocity gauge of our car, it shows us just only one velocity, right? No type of car report two velocity on the speed gauge, right? Okay. For our car, we have the speed gauge that report us just only one speed. Okay. No car report us. You drive a car with Vx equal to 40 meter per second and Vy equal to 50 meter per second. No car report like that. Okay. And no car report you that the acceleration in X and in Y. No. If you set up the acceleration gauge also for some case that if you would like to know the acceleration also, so it's report to the tangential only. Okay, so that's why if we compare with the when we drive the car, okay, so the speed is always have certainly one component for tangential direction. So for this case, 25 meters per second is always the velocity in tangential direction Vt. And also when we increase the speed of the car, we increase the tangential acceleration. Okay, this is At. Okay, and for this case, what do you think? We will use the xy coordinate to solve this problem, or we will apply the normal and tangential coordinate system, or we apply the radial polar coordinate system to solve this problem. That is maybe to give us the direct procedure to get the answer. According to this problem, we should apply the normal and tangential coordinate system instead of X and Y. Okay, you may observe it by yourself. Okay, if we solve in X and Y, you will find out it may be hard because in X and Y, when we would like to find the acceleration, okay, in X and Y, okay, in X and Y, if you know the velocity vector, okay, so the acceleration vector is equal to dv by dt, right? Okay, but for the case, you see that at this position, that is along the curve, we have no idea that at this position, the velocity in X or in Y direction, it is equal to what, right? Okay, we have no idea this time. Okay, but actually we can find, but now we don't know, right? Okay, so then it's maybe better to solve this problem in normal and tangential coordinate system instead, and after that we may convert it to X and Y coordinate again if we would like to do it like that. Okay, and for r theta also it is the same manner because we do not know exactly the angle Okay, if we set up, this is a reference point. Okay, so R is here. Okay, and it's theta. So we have the additional unknown that is R and theta here. That is maybe make us a lot of confusion for solving the problem, right? But if we working with normal and tangential direction, okay, we already have the components, okay, velocity component and acceleration component, some components, and also we have the path. Okay, so then that's why for this problem we apply normal and tangential direction instead. Okay, in order to find the acceleration, because we would like to know just only acceleration, right? Because velocity we already know. For the normal and tangential direction, velocity we have just one component. So then for v, the problem is not ask us because it has just only one term, right? So v is just only 25 t. Actually, if we write in vector form, it has only one component here. Okay, but for acceleration, now we have one component at from the problem, that is 3 meters per second squared. And we would like to find an, and it should be 1. Okay, and we know that for normal and tangential coordinate system, an is equal to v squared over rho, and rho is the radius of curvature. Okay, and we also have the path curve, that is y equal to x squared over 100. Okay, and the radius of curvature we can determine by this term. Okay, by this term, that is 1 plus y prime square power 3 over 2. Okay, divided by the absolute value of the second derivative of part. Okay, of y. Y double prime is d2y by the x2. Okay, y prime is dy by the x. Okay, according to this, we take the first derivative to y. Okay, we got this term. And we take the second derivative to y with respect to x, we got the constant. Okay, after that, we can determine for the radius of curvature when x equal to 30 meters. Okay, according to the coordinate here. Okay, we substitute x equal to 30 meters. Dot radius curvature at this point become 79.3 meters. After that, the acceleration, now we have two components already. At is equal to 3 meters per second squared. An is become v squared over rho, that's we get 7.881 meters per second squared. And so then we can find the magnitude here, that is become 8.4 meters per second squared. Then let's take a look for the direction. Okay, the direction here, we would like to find the direction angle of the acceleration that make with the x-axis. So the direction, you see that this is the path. Okay, if we compare with the path here. Okay, so we have this line, this red line represent the direction of the path at this point. That is the direction of tangent. This is a tangent direction with respect to x. Okay, that now we may represent it like the angle phi. Okay, angle phi here represent the tangential line of the path. That is we can determine by arctan dy by the x. Dy by the x is the slope of the path at x equal to 30 meters. Okay, and for the angle, we would like to find this angle actually. That is the angle theta here. Okay, that Actually, we have two components of AN and AT. Okay. So the total one is become green. The total A become green. And we can determine the angle between the total acceleration with respect to the tangential direction here. That is alpha. The angle alpha is can determine by arctan AN divided by AT. We got the angle become 69.16 degree. Okay. And the angle phi, that is the path angle. Okay. It's become 30.96 degree here. And for theta, that is this angle. Okay. This is equal to alpha, right? It's equal to alpha minus angle phi. Okay. That is after we determine alpha and phi, we obtain theta here. Okay, let's complete this problem.